Before I start back in physics, the second problem set was just due, and the third will go up soon. If you had trouble with the website, there were half a dozen of you that had website issues. Do contact the support people if you're getting error messages, and if the errors and so on cause you to be late, write me an email and we'll fix it, okay? So it's the point of this, fighting with software is the bane of our current existence, and trying to get it right is hard, and suffering with stuff that doesn't work well is a pain in the neck. But this is a physics class, not a suffering with software class, so we can fix whatever goes wrong for you, okay? Last time I was talking about, well, in the context of wheels, I was talking a lot about friction and things associated with friction. And a couple of questions came in that I either didn't notice or didn't have a chance to talk about. And I'll remind you again, asking them live is, out loud really helps make sure that I get to them. But a bunch of good questions came in. So let me go after some of them. The first one asks, isn't the coefficient of static or kinetic friction a constant that depends on the material? So to rephrase that in sort of the language that we're using here is for sliding and for static friction, the friction between two surfaces that are not moving yet relative to one another, and for sliding friction where they're moving across one another, also called sometimes dynamic friction. Those frictional forces do depend on the materials that touch one another. And I told you last time that to a pretty good approximation, the harder you press the two surfaces together, the stronger the frictions get. I think the right word to say is that you get more traction, which is the largest values of friction available to you go up in proportion to how tightly the two surfaces are pushed together. But the surfaces do matter, and you've noticed this, that some surfaces are essentially slippery and some are not. Teflon, for example, Teflon and Teflon slide pretty easily across one another. And so you're used to now having lots of household objects that are coated with these non-stick, high slippery surfaces that are tough to get serious traction on. On the other hand, there are certain surfaces that grip particularly well. For example, various types of rubber grip each other very nicely. There's a reason why car tires are made out of rubber. I mean, there are many reasons, but making it out of rubber tends to give you good traction, whereas making it out of Teflon would be a bad choice. Okay? So yes, surfaces matter. In general, the forces of friction between two surfaces rarely get larger than the forces pressing those surfaces together. It's a useful rule of thumb, probably more to physicists than to you all. But, all right? What would be an example of sliding friction being greater than static friction? And just to remind you what the story here is, that if you take two surfaces that are pressed against each other and not in relative motion yet, they're not sliding, they're static. They grip each other pretty well. Again, depends on the material, but okay, they grip each other. Once you push or pull on one of the surfaces to the point where it breaks free of the other one and begins to slide, usually the force that shows up, almost always, the force that shows up now when the two surfaces are actively sliding across one another, namely the force of sliding friction, is usually weaker than the largest value of static friction you got just before they broke free. It's almost universal. I can only, and think about it, looking at the question, you have to look for a really exotic situation to find a case where as things move, the frictional forces between the two surfaces actually goes up. And the only one I can think of is starch and water, which shows up in people sell stuff like this too. The stuff where you poke at it and it's hard, and if you go slowly, it's like it's a liquid. You know that fluids like that? You probably made them somewhere in K through 12. Something like that, a fluid like that, in fact, the name for these, what are called shear thickening liquids, or they're called dilatant. Two surfaces separated by one of those liquids. if they're not moving, they're really connected by just like a liquid that flows easily. And so at low speeds, there's almost no friction at all. But if you go fast, they will begin to grip each other more and more strongly, and eventually they sort of crack and crumble. Clay and water will do this sort of thing. Various clays will do that, whereas you go faster, they get stiffer. And so that's about the only exotic examples I can think of. In general, sliding friction is just weaker. And so if you're trying to get frictional forces to move around and do things you want to do, you typically want static friction. And that is true of wheels. There's, can I think of any example of a case where you want sliding friction in a wheel? Probably not really. I mean, maybe with drag racing stuff. But basically, you do not want the wheel to slide on the surface that it's sitting on. It wears the wheel out. It creates thermal energy, which is not going to be very useful. It sort of wastes ordered energy, which I'll come back to shortly, by turning it into thermal energy. And it typically doesn't give you as strong a frictional force as you would like. All right, so stick with static friction with wheels. Another question that came in is, why do you need a force to turn right? So I'll remind you the context in which this came in is approximately if it's an icy day out and you are riding your bicycle or you're walking or you're driving a car, any of these things, the easiest thing for you to do is to continue at constant velocity across the surface. Once you get moving, you move for free. You do not need a force to make you continue. You just need to keep going. You'll do it naturally because of inertia. If, however, you change your velocity in any way, that involves acceleration. And accelerations are caused by forces. So if you want to speed up, you need a forward force on you. And if that forward force is going to come out of the icy pavement, this is tricky, because you're not going to get very much forward force out of that icy pavement. It's slippery. If you're trying to stop, it's similarly, you need now a backward force out of the pavement to bring you to rest. And that can be tricky, which reminds me, okay, I'll take a diversion. Several years ago, we had really sort of an ice storm. It was really icy out along Emmett Street, right in front of the Memorial Gym. And a guy was crossing the street obliviously. You know, I probably pushed the yellow blink, blink, blink. And he's crossing the street staring at his phone. And I tried to stop, starting 200 feet upstream of him. And I got within about that far of him, and he never noticed me. I'm there, sliding across. I need backward force, and I don't want it to be him exerting a backward force on me. I don't think he ever realized that anything happened. Anyhow, so starting, stopping, tough. Turning is tough as well. Why? Because if you turn, you're not moving at constant velocity. You know, this is the ultimate turn, right? Go in a circle. I'm not moving at constant velocity. I'm moving at constant speed, but my direction of travel is just going from to your right, away from you, to your left, toward you, and so on. I'm accelerating. So turns are just as big a problem on an icy surface as starting and stopping. And that's why, you know, vehicles go off the road at turns. And they typically go off the road on the outside of the turn because that's the way inertia takes them when they lose traction. Okay? The guy texting, I'm about to get hit. Sorry. With the box, a question a little bit about the sliding box here, and I asked you the question that when the box skids to a stop, which object does work on which object? The box is unable to do any work, either positive or negative, on the table because the table doesn't move. You can't do work on something that doesn't move. You can't do work on a wall, the floor. You know, okay, they move a tiny bit if you hit them hard enough. But for all practical purposes, they don't move, therefore you can't do work on them. The box, on the other hand, or the wagon, is moving. So there's every opportunity to do work on it, positive or negative. And in this case, the table pushes the wagon to the left as the wagon moves to the right. That's the recipe for doing negative work. Okay? So the table successfully removes energy from the box, the box is unsuccessful in transferring any energy to the table, which creates this weird situation where the energy seems to disappear. Well, it didn't. It got chopped up into little bitties and sprinkled around the surfaces where it shows up as thermal energy. It's hot. And you know from rubbing your hands together, right? You know, why does it get hot? It's because you're turning work. If you think about it carefully, you'll realize you're doing work on parts of your hands, and the work is disappearing. Or at least there's negative work being done on parts of your hands. Where did that energy go? It's showing up as thermal energy, and you can feel it. All right? And I'll talk a little bit more about thermal energy when I get done with, am I done with these? What is sliding friction versus static? Static is when the two surfaces are moving at the same velocity. They're not in relative motion. It's static. Nothing's changing. Sliding is when they're actually going across each other. They have different velocities. And the last is, it asks me about what's a lever arm, to remind you what a lever arm, because it showed up in your problem sets for today frequently. Lever arm it's a vector. It's the distance you are from a pivot, or a center of rotation, the place you're considering something rotating about. So how far are you away? And it has a direction to it too. The direction of the lever arm is from the pivot to where you are pushing, for example. Okay, so that's lever arm. And you use levers in everyday life. You may not think about them very much. You know, opening and closing doors, they're all levers. Scissors are levers, whatever. Okay, so I think at that I'm going to stop and go back to the mainstream here, which is, I just reminded you that when you rub your hands together, it gets hot, and if you figure out work being done, you'll discover that negative work is being done on your hands, and that work doesn't seem to show up somewhere else. It goes away. It's thermal energy, and it's in the atoms and molecules, the very components from which your hand's skin is made of. They're jiggling around faster than they were before. They are always in constant motion. So everything in this room because everything's got temperature. It turns out temperature and thermal energy are related to one another. Everything's got thermal energy in it. So microscopically, everything's jittering, jiggling around. They periodically, the atoms and molecules have kinetic energy whenever they're in motion. They have potential energy whenever they're sort of bumping into each other and rebounding. And so that they're in constant action. And that energy, because it's dispersed among all the particles, statistically, it's hard to get it to do anything interesting directly. It cannot reassemble from all the individual atoms and molecules. It can't get back together to get the entire object to suddenly have, for example, kinetic energy. So to put in a specific example, a ball sitting there, it's got tons of thermal energy in it. Plenty of thermal energy that if all that thermal energy became kinetic energy, it could probably leap off this table to the ceiling. Someday I'll calculate that. It's somewhere easily that range. But why doesn't it do it? Why doesn't all the energy get its act together and cause the ball to leap upward? It would suddenly become a cold ball that leaps to the ceiling. The reason for that is all statistical. The statistics of getting that stuff to come back together is like unstirring the colored beads that I was playing with last time. You can't unstir it. Once you've done it, it's done. Getting it reassembled back the way it was, it can be done, but in the process of doing that, you create disorder somewhere else. So it's a one-way street. And our existence, the way we live our lives and how time goes by for us and stuff, is in large part caused by the gradual drift from an orderly arrangement of the world around us to a less orderly arrangement of the world around us. We're going downhill in order, less and less and less order. And toward that end, I've got a question to ask you guys. And Get the buttons, all the buttons. So the question is this. Suppose I've got 4 photographs. They're pairs. So they're pairs that show the Q and R pair. In the Q pair, you've got an isolated room. These are photographs of something that's sort of in isolation. An isolated room with dry air and a full cup of water. Those of you who were in Physics 1050 last semester, these are easy questions. Full cup of water. In the other photograph of the pair, it's the same exact collection of stuff. However, now the room has moist air and the cup's empty. So all the water molecules are still there, but they're not in the cup anymore. They're out in the world. Okay, so 2 photographs. They're the same stuff, arranged differently. The other pair is a cooler temperature, a thermally cool whole vase sitting on a table, maybe with flowers in it. And the other photograph in the pair shows exactly the same stuff, but now the vase has fallen off the table, it's smashed on the floor, and it's gotten warmer as a result. So can you envision those 2 pairs of photographs? One is a before and one is an after in each case. One leads naturally to the other as time goes forward in time. And the question is, which of those is the more disorderly arrangement? Which photograph within each pair is the more disorderly arrangement? And the advice I'll give you before having you answer it, just make you think about this, is that the world tends to create more and more disorder. Things do not go from disorderly to orderly without intervention from outside, and we're not intervening. We're leaving these things in isolation. Are you okay with the question? Remember, it's not the world's best posed question. This is sort of the underlying, the connection with this is the world of thermodynamics, which is a 1050 topic that I'm just giving you a taste of, a little piece of. Okay? So which is the most disordered arrangement? We'll go to 40 seconds and then call it. Three, 2, 1, 0. C it is. Yeah. What C is, to remind you what C is the more disorderly arrangements are the room full of moist air in an empty cup and the warmer smashed vase on the floor. And the reason this is interesting is there is actually a measure, a physical quantity that measures disorder precisely. It has important meaning to physicists certainly and to scientists in general. The measure of how much disorder a system has is known as entropy, not energy, entropy. It's a completely different, not conserved quantity, but in effect it's always increasing, which is a little bit too short a statement, but there are details that I'm sweeping under the rug. But things tend to go to more and more disorder. Undoing the disordering process is tough and inevitably involves creating more disorder somewhere else. So our world is always going towards more and more disorder. We receive some order from sunlight, but in general, we just keep turning things into disorder. Mining minerals that were relatively orderly and putting them in landfill, which is relatively disorderly, and so on. But a way you can observe the increase in disorder is by time ordering a bunch of photographs. If you get a box full of photographs, all the same situation, and nothing's come in to intervene and clean things up, if you put them in time order by looking at it, here now the cup of water and the air, for example, the cup is full of water, the air is dry, that's pretty orderly arrangement. Another photograph of where the water's evaporated into the air, You know that comes after the first one. The first one occurred at 1 o'clock. The second one occurred at 2 o'clock. The water evaporated. It doesn't unevaporate, except, in normal situations, it doesn't unevaporate, which is to say that process of letting the water leave the cup and go and mix with the room air creates disorder, which cannot be undone. It's a one-way street. The same with the smashing the vase. It had gravitational potential energy, nice and orderly when it was sitting on the table. It was structurally orderly when it was sitting on the table. It has now fallen off. It has turned its gravitational potential energy into thermal energy, which makes it hotter and more useless energy-wise. And it has lost the orderliness of a properly made vase to become a pile of glass rubble. Yeah? If the vase had fallen off the table and stayed intact, would it be warmer or would it be cooler? I mean, how would that affect the temperature? It actually takes energy to tear apart the structure of the vase. Work is done to pull each side and take it. So it actually would probably have ended up warmer if it had hit and bounced and settled. So the amount of disorder in a system is not just in the thermal energy. It's also in the structure. So measuring the disorder of an object is a complicated process, a complicated task. But yeah, and actually is another example where temperature gets kind of interestingly involved in this story is that glass of water evaporating gets colder. Evaporation chills you down, right? You get water on your hand and it evaporates, you feel cold, because it takes energy to separate the water molecules and send them on their way. So despite the fact that in the story, situation R is actually a little cooler than situation Q. There's a little less thermal energy around in situation R. Nonetheless, it is more disorderly. The disorder isn't thermal, it's in the mixing of the air and the water. You've got them all mixed up now. How you can get them apart? It's like sock drawer, one of my favorite analogies. A sock drawer, you got the orange socks and the blue socks all separated. That's orderly. You give it a good shake, orange and blue socks, right? How are you going to get that undone? Hard. Okay? So having talked then, let me stop this guy, about the degradation of energy as the loss of order in our world is just sort of a universal process that goes on. It happens specifically to energy, and it's a big deal for us and for living on Earth. There is tons of energy around. There's no shortage of energy. Problem is a lot of it's thermal energy, which is, it's not like you can't do a thing with it. It's tougher to work with. It does not all, there are rules governing how much work you can get out of thermal energy. And so all the suffering we're doing now over fossil fuels and energy in general and the climate change, all that, it's all about order. If we could only reorder thermal energy, we'd have tons of it around, no problem. So the sort of the energy crises that have been around since the 70s, at least the 70s, they're really an order crisis. It's about you need the order rather than just the energy itself. All right? So a few last notes about energy, the various forms. Let me just remind you. So energy is a conserved quantity. It's one of three I'm going to talk about today. I'm going to get onto the other two today when talking about in the context of bumper cars. It does not have a direction, so it's just an amount. It's what's called a scalar quantity as opposed to a vector quantity. It's not a vector, it's an amount. And what makes it interesting is it's conserved. And it has two main classes. One of them is the energy that is in a moving object, kinetic energy. And the other is energy that's in the forces between or among or within objects. And that's potential energy. And more specifically, there are a variety of potential energies. which I'll play games with in a second. But let me then remind you again that thermal energy isn't another type of energy altogether. It's just the previous two chopped up into little bits. So I said I would talk about the types of energy a little more just for fun and games. So there's energy in a moving object. If I push on it, if I push on the ball and it moves the distance, the direction of my force, it becomes kinetic energy, right? If I, so kinetic energy is in the movement of an object. Kinetic energy is indifferent to the direction of the movement of the object. So the object, I can't catch and talk. I can't catch it by itself, but catch and talk too hard. So whether the ball is moving to the right or the left makes no difference to the energy. It's purely speed dependent. And actually, for practical purposes, you should know that the kinetic energy in an object is proportional to its speed squared, which is why fast-moving objects carry a lot of kinetic energy compared to slow-moving objects. As the speed increases, whether it's, the example that leaps to mind is cars. At 30 miles an hour, a car carries 1 unit of kinetic energy, let's say. At 60 miles an hour, that's twice the speed, it carries 4 units of kinetic energy. This is why high-speed collisions between anything are dangerous. So the energy is going up fast. All right? Okay, so that's kinetic energy. The energy that gets stored in forces, first example is the energy stored in the force of gravity between the ball and the earth. As that ball is going up, after I've thrown it, when I threw it, I was taking energy out of me and giving it to the ball. We can do that, but let's leave that. The ball now has kinetic energy. It rises upward to peak height. As it does, it's converting its kinetic energy into gravitational potential energy. It's sort of stretching the force of gravity. And so at the top, the ball is briefly motionless. Remember the old story? At that point, it has no kinetic energy. It's all stored in the gravitational forces. We assign all that energy to the ball, although it's really shared by the ball and the earth. The earth can't do anything with it, really, because it's so massive. The earth just doesn't move. You can't do work on it. You can't do negative work on it. All the energy goes, really, all the gravitational potential energy is kind of acts on the ball, so we sort of say the ball has it. It's not between the two. It's a sort of a shorthand. It's a little bit of a cheat, but it's fine. The ball has lots of kinetic energy, lots of gravitational potential energy, and now none. All right? Other potential energies that are around. So these are some of my favorites. Did you ever have a can of mixed nuts like this when you were a kid? I did. Actually, my grandparents did. And they let me do this, like, hey, Grandpa, look, you want some mixed nuts? Ah! It was packed, not only is it chock full of a snake, but it's a spring. So to get the snake in there, you have to do work on it. Shove it in and move it in, okay? So I just did work on the snake, and it's stored here. No motion. It's basically you call this elastic potential energy. And I would do this over and over again, right? So the same person would once again be surprised. All right? We will, this semester, be spending some time with the forces between and among magnets. And you guys are fortunate to live in an era when there are really good, inexpensive, very strong magnets around. So these magnets, rare earth magnets, are strong enough that this guy's finding the metal pieces in the table. So working on this table is problematic because it's got pieces of steel in it. But if you get these guys close enough, they will leap at each other. So there's energy stored in the, well, these guys are pushing apart. Let me turn around. Okay, they jump at each other. And anyways, so there's energy stored in the forces between magnets. What other ones do? Okay, this is really my favorite here. Again, those of you who were in 1020 know this story here. This is a device which we will encounter later in the semester. is known as a capacitor. And what it is essentially, although it doesn't look like it, it looks a big cylinder, it's two surfaces of, two conducting surfaces, two essentially metal surfaces that are separated by an insulator. So you can put electric charge on them. And we're going to be doing electric charge this semester and very soon. So you can put, for example, positive charge on this side and negative charge on this side. They love each other. They attract each other. They're happy to be as close as possible. They would actually prefer to get together if they could. So there's a huge attraction between those two charges and therefore on the two surfaces. And if you allow them to get together, they will do a lot of work in the process. So they will release a lot of energy. They have stored energy when they are sitting, positive charge on one side, negative charge on the other. They have a lot of potential energy. It's, to give it a name, it's called electrostatic potential energy. The energy stored in the electric forces between motionless objects, the static part. So I'm going to do that. I'm going to put positive charges on one surface and negative charges on another. There will be no overall charge on it, which is good, because if you get lots of overall charge on an object, it tends to leave violently by way of sparks, which we'll do also. And so I would get shocks all over the place, but I'm not going to do that. I am going to put positive charge on one side and negative charge on the other, and I'm going to do that with the help of a collection of 9-volt batteries. So this is a whole passel of 9-volt batteries. And what batteries do, which we'll also see, is they move charges from one place to another using chemical energy to do it. So they're actually doing work on the charges, piling up the positive ones on one surface, piling up the negative ones on another. The very existence of positive and negative is already an interesting thing that we'll have to look at. But we've now piled up a whole lot of them on each of the opposite surfaces. And the amount of surface that is present inside this cylinder is amazing. You know, it's football fields of surface hiding inside there. And I'm going to let them get together. All right? Ready? Get set. They like getting together. Again. This, incidentally, is one way of spot welding things. So those of you who have ever tried to connect two pieces of metal together, this is a technique that's actually used to do it. Not quite with a screwdriver, but that's the idea. It does take time. The batteries are being, they're suffering over this. Oh my gosh, you're making me move another charge. Oh, it's so hard. They will actually run out of stored energy. Their energy is in there in the form of chemical potential energy, and they're using it up. And now it's all in this device. Ready? All right. Fun. All right. With that, I'll stop talking about energy and go on to go back to wheels. Okay? Halfway to its peak, what kind of energy does the falling ball have? Kinetic, gravitational. It's a continuous conversion. As the ball is going up, at the moment it leaves my hand, it has as much kinetic energy as it will ever have. At the top of its peak height, it has as much gravitational potential energy as it ever had. Because nothing is touching it between leaving my hand and it reaching peak, it doesn't do work on anything. So whatever energy it has, it has. It can't get rid of it. It's stuck. But the energy is converted continuously from kinetic at the moment it leaves my hand to gravitational at the top, and smoothly between the two. So if I play graph, here's the graph of kinetic energy, gravitational potential. It starts with no gravitational, lots of kinetic, and as it rises, whoosh, they go together. So if you sum its kinetic energy plus its gravitational potential energy, steady constant, same. Okay? Back to wheels. This wheel-less wagon obviously suffers from a lot of friction problems. If you get it moving, it always experiences sliding friction, which wastes energy and wears out the bottom of the wagon and the top of the pavement. So what can you do? Well, the primitive solution is to put rollers underneath. And if I put rollers under the wagon, it now can coast because the net force on it's essentially zero, very close to zero, and it's no longer wasting its energy. But there is still friction around. If you look at the top of each roller as it encounters the wagon, it lands on it touches the wagon moves as the roller rolls, and then that surface that was just momentarily touching the wagon pulls away essentially vertically. So there is contact between the two surfaces, but no relative movement between the two surfaces. They're experiencing, to some extent, static friction. So there is friction, it's just static friction. And I consider this sort of touch and release. When a surface lands and lifts. And that is present not only in rollers, but it's also present in wheels. So the problem with rollers themselves is that they come out the back of the vehicle, and you got to put a new one in front. You need 3 of them. I mean, it was probably not any fun to be a person working on the pyramids. Okay, they surely used rollers, but you kept moving the rollers from the back to the front. Back, not a very good approach for like a car. So long and short of it is cars operate on a more sophisticated device called a wheel, which probably does get reinvented even if it's... what a wheel does is it lands and leaves, but it stays with the vehicle, which is good. I won't talk about all the issues of bearings and how you manage to get the whole thing to stay together. But if you have a properly developed modern wheel, has no sliding friction to speak of. It's all static friction. And the point I want to make here is that if you look at to pick a spot, that red marked spot, right? It lands and then it lifts. It doesn't slide across the surface. This would be sliding. But it's touch and release. And that means the two surfaces, the rubber and the table, they do come into contact. They can, which is good, experience static frictional forces while they're in contact. But they don't slide across each other, no sliding friction. Why would you even want static friction? Suppose you're turning, or you're speeding up, or you're slowing down. Now you actually do want these two surfaces to push against each other, but you want a static frictional force. So when you're speeding up in a car, slowing down in a car, or turning in a car, you are having the pavement exert forces on the car, frictional forces on the car, to speed it up or slow it down or turn it. And having them always be static frictional forces is good. Less wear on your tires, less wasted energy, and better grip. If you begin to skid in various ways, which is, alas, not uncommon, you lose, among other things, the grip is worse, you wear things out, you create thermal energy, and finally, you lose direction control. Like if you're turning, you want the ground to push your wheel to the side with static frictional force. And so you turn the wheels, you aim the wheel such that it gets a sideways static frictional force on the ground. And that's all good. If you start skidding, you lose the sideways. Sliding friction is very specific. It tries to bring the surface that's sliding across motionless pavement to a stop, which means it pushes it opposite its current velocity. And that's your only choice. So you go from using a wheel, You go from using a wheel that's trying to turn you, right, to operating on basically a skidding bumper. It has no direction memory at all. You'll go straight and skid that way. So avoid sliding friction in the car. Okay, any other questions? All right. That's good enough for the story of wheels. Let me go on then and talk about bumper cars. And the reason to talk about bumper cars, well, a reason, is they're beautiful colliding systems where you get objects bumping into each other and passing along two more conserved quantities. And I'm not going to get to do proper justice to the second of them, but the first one is, I probably can do decently. The first quantity that sort of that governs a lot of the behavior of bumper cars, and hopefully you've all ridden bumper cars, is another physical quantity known as momentum. And momentum, it's a conserved physical quantity, so it's super duper special. It has to do with the velocity of an object. An object carries momentum with it. Because it's a conserved quantity, you can actually have it and keep it. And when you're carrying momentum with you, that momentum has two characteristics, two parts to it. It is a vector quantity, so it has an amount, how much momentum you're carrying, and it has a direction, which way your momentum is pointed. And the direction is crucial, important, it matters a lot. And to show you what kind of role it plays, let me show you myself. I will carry momentum with me, and I'll tell you in advance that momentum, like energy, can be calculated based on physical quantities we already know about. And it turns out that the momentum an object carries is its mass times its velocity, and it points in the direction of that velocity. So when I'm carrying momentum, I will be moving. You can't avoid it. Your momentum is proportional to your velocity. All right? So I'm going to start with no momentum. And I'm going to stand on a wheelie cart where it says do not stand. And the point is that right now when I'm motionless and my velocity is 0, I have no momentum. And no momentum, it being a vector quantity, no amount of a quantity that has a direction, is just, what's my direction? Doesn't exist. I have 0 momentum, and it's in no particular direction. I'm going to get some momentum, and I'm going to get momentum to the right. And to get it, I can't create it. It's a conserved quantity. I have to get it from something else. So I'm going to get it from the wall. I'm going to let the wall push me to the right, and I'm going to make the wall push me to the right by pushing it to the left. And in doing that, I'm going to give it momentum to your left, which you will barely see, well, you won't see because the wall is too massive. Remember, the wall's momentum is its mass times its velocity. It's got so much mass, there's no velocity. It's connected to the earth, the whole mess. So, but I'm going to give it leftward momentum. It's going to give me rightward momentum, an equal amount because momentum's conserved. If I grab 12 units to the right out of the wall's going to have a deficit of 12 units to the right, which is to say it's going to have 12 units of momentum to the left, which you won't notice, but that's it. So I'm going to get some, and I'm going to carry it with me. Ready? Get set? Right. So I'm carrying it with me, and I can't stop because I'm carrying the momentum. And these carts never go quite straight, and friction's always around, so I didn't manage to get the whole way across the room, and at least I didn't fall. Okay. The point is that once I get it out of the wall, the real reason why I can't stop, and the real reason why Newton's first law of motion is what it is because momentum's conserved. And once you got it, you can't change it. All right. Do I have enough to make it across the room? Oh, I'm going to hit things. Collision. All right. I gave it to the chair. But the idea is that you get it, you carry it with you. And this is, you can think of this with bumper cars. In the world of bumper cars, you're often gathering momentum. You have to accumulate. It takes a little while to accumulate. You might initially get it out of the floor with the help of motors. And then when you smash into somebody else, I'm careful. I could give it to somebody else by hitting them. And I would lose it, and I might well come to a stop. And they would now have it. I'm going to hit the stair. So I gave it to the stair. But the point is, you sort of feel like it's something you have. You do not carry force with you. It's common language that people often talk about. Wow, that such and such was moving with tremendous force. No, it was moving with tremendous momentum. That's what you carry, the conserved quantity. In the act of transferring it, you use forces. So I told you with energy, the mechanical means for transferring energy was work, right? You do work on something to take energy out of you and give it to somebody. The same kind of idea is present with momentum. How do you give momentum to something? You do it by exerting a force on them for a period of time. A process is called impulse. So to give momentum to something, for example, when I was having the wall give me momentum to the right, I was having the wall do an impulse on me, which is to exert a force on me for time. And suddenly I had the momentum and off I go, across the room, and I can't stop. I mean, of course, I'm friction and all sorts of nasty things not working quite right sort of spoil the clarity of the situation, but that's the idea. You get momentum out of something by way of an impulse. You give it to something else by way of another impulse. So those are that's the process. And the momentum that's transferred can be transferred by way of a big force for a little time or a little force for a big time. It's the product of the two that matters. The force times the time. So for example, how does hammering something work? I've talked about hammering before, but if I got a nail, so this is a roofing nail, and this is a hammer, official league. So this is what a lot of people play with in a sport called baseball, right? It is an object that when you give it momentum and have it hit something, it will transfer that momentum very, very quickly by way of an enormous force. And so the story here is, if I get these two balls moving, they have the same mass, I get them moving with the same velocity, they carry the same momentum. And they will transfer that momentum to something in the process of stopping. So both, when they hit, they try to transfer, in this case, they're both heading down with 6 units of downward momentum. And they both gave away that 6 units of downward momentum by way of a force times a time. And the difference is one of these has a softer surface than the other. This one is not a league one. It's more of a soft, reduced impact force type. So the demonstration part of this is as follows. This is a league baseball. If you're ever short on hammers, it's just fine. It transfers its momentum to the nail by way of an enormous force for a very short period of time. Because the surface is so unyielding, it has to come to a stop quickly, otherwise the nail and it will occupy the same space at the same time. So the momentum comes out of the ball, goes into the nail very suddenly. Whereas with a slightly softer surface, you can't pound a nail in, okay? Public service announcement. For grown-ups, maybe playing with league balls, fine. For children, not so good. Be thoughtful. If you send kids off to play with a ball like this, if it hits, it transfers its momentum really fast by way of huge forces. And we go through life trying to avoid sudden transfers of momentum. In the middle of the night when you're going to get a snack at the refrigerator, you hope you do not walk into a cement wall. You will transfer all your momentum to the cement wall too fast by way of a big force. You much rather hit the beanbag chair or something like that takes the momentum out of you slowly by way of a small force. Okay, that's enough for Wednesday. We'll go back to things on Friday.